Yeah, so I'm Mona Trick. I'm treasurer of APS and also chair of the Paleo 2025 committee. We'll start first with our acknowledgement. With gratitude and reciprocity, we acknowledge the relationships to the land and all beings, and the songs, stories, and teachings of the Tsujita Nation, the Pikai Nation, the Kenai Nation, the Stony Nakoti Nation, consisting of the Chiniki, Bearspaw, and Good Stony Nations, the people of the Tsujita Nation, and the Métis. So with our first speaker is Dr. Cam Tsujita, is the Associate Professor in the Department of Earth Sciences at Western University in London, Ontario, where he teaches several undergraduate courses in geology, and he coordinates much of the public outreach activities offered through the department. He received his PhD in geology at McMaster University in Hamilton, Ontario, under the supervision of the late Gerd Westerman. His current research focuses on taphonomic and palaeoecological studies on Paleozoic invertebrate marine communities. Much of his presentation today will focus on aspects of his earlier research on Cretaceous ammonites with updates on the main findings of those studies.
Thank you, and thanks for the invitation to speak to you today. It's a pleasure. I will sort of preface this in saying that this will be almost like a lifetime study. It's more about curiosity than anything else. And I'll start with where it sort of began. So how did I come to study ammonites? And this sort of began back a long time ago. So what do you want to do when you grow up? And I couldn't really answer that because I didn't know a word for it. But it sort of started here. And I grew up in Alberta. I'm from Olds originally. And since I can, as far back as I remember, I've been collecting fossils and collecting rocks pretty much my whole life. So this sort of started at about age 4 in Alberta. I can say now that even throughout all this time, I've known maybe marginally more than I did back then. Here's age 6 to 7 along Milk River. This is in Joggins, Nova Scotia. And around this time as well, I developed also an obsession with marine biology. And that sort of melted together. And we moved out to Ontario a little later on. And by that point, it was like, well, Ontario doesn't have any dinosaurs, though. So that sort of nixed that. But we did have a lot of invertebrates. So that's where that interest in invertebrates came from. So I eventually ended up going to Western, where I am also teaching now, and learned more about not only just paleontology, but I got a much better appreciation of the place of paleontology in geology in general as a context. And strangely enough, I did my senior thesis on trilobites in the Collingwood Shale in Ontario. And this led to applying to McMaster University, and this was going to be a project on the stratigraphy of the Bearpaw Formation in the southern Alberta. Now that interest in the Bearpaw, of course, started when I was very, very little. And in retrospect, it's kind of funny to think that this is how it sort of panned out. So I proposed my own project. I was accepted by Dr. Gerd Westerman, who was also a preeminent expert on ammonites, not on Cretaceous ammonites, but mostly on Jurassic ammonites. But he was one of the few people at that time as well who was thinking about ammonites, not just from a biostratigraphic context, but also thinking about their ecology, thinking about how they lived and that sort of thing. And the project itself, I came sort of up with an ultimate excuse to do the project from a very maybe more practical perspective, and realized that there had been very little done on the stratigraphy of the Bearpaw since about the 1960s. So probably worth an update. By this point, it was in the 90s. So I thought, well, maybe it's worth taking another look from a modern perspective. So the main task of the PhD project in general was to basically look at the stratigraphy of the Bearpaw Formation, basically to map the main outcrops, to measure these outcrops, correlate the sections, and then sort of figure out sort of a general story about this particular unit. This was using ammonite zones that were defined in the U.S. for the Western Interior Basin. So if we go back to Lake Campanian in the late Cretaceous, sedimentary rocks, of course, were deposited when North America was covered by the Western Interior Seaway, stretching from the Gulf of Mexico all the way up to the Arctic Ocean. And in our sort of corner of the world here, We have, and here are the sort of main points of interest from a cultural viewpoint. But we can see that most of the province is underwater. Most of the Alberta and almost all of Saskatchewan would have been underwater as well. So we often are thinking about all the dinosaurs that were prancing around on land and along this coastal plain. But something that I was always really interested in was not so much what's happening on land, but was also what was actually happening in the sea. And this is something that, that the Western Interior Seaway now, there's a lot of sedimentological studies that are now sort of focused on units of marine successions in here, but it was given sort of relatively little love at that point. So that's what I set out to do. So among the many, many marine animals that lived in the seaway were ammonites. So then what are ammonites? So ammonites are extinct shelled cephalopods in the same general group as squids, cuttlefish, octopuses, nautilus, and so on. And ammonites are members of the subclass Ammonoidea. So strictly speaking, we should be calling them ammonoids, and ammonites as only being part of the Ammonitina, which is a smaller group. But it's easier to call all of them ammonites. We know not a whole lot about the soft parts of ammonites. They're assumed to be similar to squids and nautilus and octopus and that sort of thing, just because we are aware that they were cephalopods. So they probably look fairly similar. And the range of ammonites, or more properly ammonoids, ranges from the Devonian up to the end of the Cretaceous period and went extinct at the same time as the non-avian dinosaurs did. Ammonites had a chambered shell that's assumed to have been functionally similar to Nautilus, working both as a natural sort of submarine as well as a submarine jet fighter, if you will. Of course, ammonites for many, many years are known to be very important index fossils. They can be used to date intervals of strata. We can sort of divide these up into slices of time and be able to correlate stratigraphic units that way. This was the basic approach that was taken sort of at the beginning of this project. And here are the main places where the bear paw crops out, or places where, at least if you measure all the sections, you can get up to something somewhat resembling a complete section. Not always successful at that in that way, but we can get a fairly good coverage. A lot of exposures were studied, basically noting the characteristics of the rocks, the fossil contents, and looking at the occurrence of specific ammonites that were used to identify these ammonite zones. So among these various places, start from west to east, we have Lundbrick, St. Mary River, of course, and many berries down in the southeastern corner of Alberta. Also, a number of exposures from south to north here. So there's Del Bonita, the Old Man River, the Little Bow River, Actually, this should have been St. Mary's as well. The Bow River, the Red Deer River, and the Battle River. And a lot of people are familiar with the exposures in around the Lethbridge area, but the bear paw does crop out in a lot of different places. Different species of Baculites specifically were recognized. These are fairly easy to recognize. These are the straight shelled orthoconic ammonites that can be recognized on the basis of their pattern of sutures, of their ribbing pattern, as well as the cross-sectional shape of the shell. And this can be a little bit subtle, but we can see that there are distinct differences between them. And for example, between the compressus and cuneatus, you can see that cuneatus has a triangular shape. Rhysidae has a flatter shape with a more developed keel, and so on. So even where the sutures aren't particularly visible, at least the cross-sectional shape is a fairly easy way to recognize them all. So we are mostly concerned here with the zones representing compressus, cuneatus, and Rhysidae. So this is how I went about doing it, from west to east and south to north. Measured a lot of rock, and the actual sections are from these black sort of bars in here. That's the actual outcrop coverage. And we can see that they represent various environments from deeper offshore up to delta or shoreline type environment, and then to not quite to onshore, but fairly close to that. And we can divide these fairly easily into ammonite zones, into these baculite zones. From south to north, same sort of thing. We could see how the facies sort of grade into one another from south to north, being mostly marine for a longer period of time in the south, and becoming increasingly more marginal marine up towards the north, and dividing those up as well, according to the occurrence of various species of baculites. As a side project, and again, the way that I pitched the project was much more sort of from a stratigraphic point of view. From my own curiosity and what I really wanted to set out to do was to look at how and where different types of ammonites lived in the Western Interior Seaway. Again, this sort of goes back to the times when I was visiting my grandparents and other relatives in around the Lethbridge area. You might be familiar with the fact that there's a very large Japanese community down in Lethbridge. So I was visiting them fairly frequently. A couple of aunts and uncles took me down into the coulee, and I'd be collecting bits and pieces of ammonites, which I didn't realize at the time, but would turn out to be a fairly lucrative gemstone industry for a lot of people eventually. But in any case, these were the very same ammonites that I was so fascinated with when I was little. At this time as well, there wasn't a whole lot that had been studied in terms of the ecology of ammonites. One of the reasons why as well is that compared to other invertebrates, many of which were ben-thic, right, lived on the seafloor. Things that live on the seafloor leave tracks and trails and things that tell us sort of what they were doing. Ammonites, which were swimmers or floaters, didn't leave that type of information. So at that time, it was like you could say that ammonites, walked on land, and nobody nobody could absolutely prove you wrong, right? Because there's very little known about the life habits. Actually, you could say that because obviously they're marine, but you know what I'm trying to say. So the idea was did they all do the same thing? Were they all swimming around like nautilus? Did they live in the same parts of the sea? Did they live in different habitats? And all these questions as to if we look at an animal, one of the first things we think of is what does this thing do, right? What does this thing eat? And that sort of thing. Now, looking at ammonites in general, especially looking at the heteromorph ammonites that have all these crazy shapes, right? This suggests that the diversity of shapes in itself suggests that there must have been differences in their life habits, and therefore would have had different habitats as well. I don't think you have this sort of such a big range in shape to and think that they were doing exactly the same thing. There was a reason that they had a different shape. That was one of the main ideas that I wanted to sort of look at. For this, I adopted kind of an multidisciplinary approach to address these questions. What are the types of things that we could use? What are the types of tools that we had to actually determine, for example, how deep the water was that particular forms lived in? What was the temperature of the water? These types of things to perhaps make up for the fact that we don't have prints of them on the seafloor. First, how do we know how ammonites look like, how they lived? And there are some possibilities that we can draw from studying the living nautilus, the chambered nautilus, which had shells that are very similar to those of ammonites. We can take a look at nautilus that live in the South Pacific and the Indo-Pacific, and this is our friendly neighbor, the nautilus, neighboring to the ammonites, of course, living in this general area of the world. And there's at least 6 species of nautilus that are now recognized to live in this general region. And much of this research was carried out by Peter Ward, who was actually another student, one of the first students of my former PhD supervisor, Garrett Westerman. I was his very last student. Peter Ward has a very long legacy. So what did they do? How did they swim? We can take a look at nautilus, and we can determine that basically, a nautilus will take water into the cavity, basically on either side of the head. That water is forced out through a funnel, below the arms and below the mouth. And swimming is accomplished basically by jetting water out, rocking backwards, and then rocking forwards, and then doing the same thing, rocking backwards and rocking forwards, and so on. And this the direction is controlled by moving the tip of this funnel. So Nautilus can move fairly well backwards, and can also move forwards a little less elegantly, but can also be moved forwards. And this is basically by moving the direction of that funnel, as you can see here. Squirt, rock, and so on. And I think there's a view here where you can actually, so the funnel you can see down here. And in this case, it's sort of aimed downwards. So it's moving slightly forwards. And here we see, again, the hyponome or funnel in this. There we go here. So that's its main way of getting around, basically what we would probably refer to as swimming. But Nautilus also works not only maybe like a jet ski, but also like a submarine. So chambers within the phragmocone part of the shell, basically the part of the shell that has these little chambers in the back, work like ballast chambers in a submarine. So in a submarine, when the ballast chambers are filled with water, basically the submarine sort of floats upwards, right up to the surface. And if you want the submarine to sink, basically you take the air out and you fill it with liquid, and then the vessel will sink. And that's sort of the similar way that we think that nautiloids did it. Basically, at night, Nautilus will fill its chambers with gas, will remove the liquid to rise towards the surface. So this is at night where there are not a lot of predators around at the surface, so Nautilus can actually rise up. During the day, to avoid predators, Nautilus will fill its chambers with liquid, remove the gas, and basically sink as the overall density of the animal will increase. Nautilus can dive to fairly significant depths, down to, I think it's something like 700 meters. Very, very impressive. Now, at the same time, because we're dealing with something like a submarine, the chambers basically that are holding that pressure, are holding up the shell and holding up against the pressure, has the danger of implosion. And we can think of an incident that happened a couple of years ago involving a few billionaires where that actually did happen. So Nautilus is a natural, maybe an analog to a submarine in many ways. And like a submarine, will face the danger of implosion if it goes too deep. So the maximum depth that it can actually live is determined by the strength of the septa, or basically these chambers, or the walls of the chamber, against implosion. How can the strength of septa be maximized? And this is where we can turn back to the ammonites and look at how the same problem was solved in different ways. So there's a couple ways of doing this. With Nautilus, the septa are very, very simple. They're like spoons. They're very, very simple. They're also very thick, right? So the thickness of the septa are an effective means of preventing implosion. All of these septa, of course, are connected by this tube, or all the chambers are connected by this tube called a siphuncle, which will allow the exchange of gas and liquid to and from the chambers. If we look at an ammonite, ammonites had thinner septa, but their septa were frilled. They were corrugated. And if you can imagine taking like an index card and bending it, right, it's fairly easy. You'd need a fairly thick index card to prevent it from buckling if you're trying to bend it. This we can sort of think as maybe more like corrugated cardboard. So you can take a relatively small amount of material, you can frill it or you can corrugate it and make basically a stronger structure from it. And this is what we see in here. And the intersection then of the septa with the outer wall of the shell, this is why we have those very, very complex looking sutures when we have fossils and the shell wall has been rubbed off. This is why we see these very sort of fractal looking septa. We have very thin frilled septa, and ammonites, they basically sort of address the same problem. They've come up with two different solutions for the same problem. We can see this in here as well. So this is where the septa intercept the cell wall of the shell wall. And here we can see where the septa intercept the shell wall over here, and we can see how this sort of frilling, right, is what we see from the outside. And these patterns are features that are unique to individual species, and so are important in probably the most important trait in terms of identifying, used to identify different species. If we can take a look at the morphotypes, basically the general shapes that we see in the Bearpaw Formation, these ones would be probably most familiar to most of you, which would be Placenticerus. These are extremely large. A couple of very large forms, including Placenticerus mici and Costatum. Costatum tends to be maybe a little bit fatter, and have a few tubercles around the umbilicus, but functionally probably fairly similar. We can see over here that it is flat, right, if you look at it from the front. So we can think of this as being sort of very similar to like a frisbee. Over here, this is a smaller form that is called Placenticerus intercalari. This is smaller, on average, is between 10 to 20 centimeters diameter. I didn't realize it at the time because I was a naive PhD student at the time, but Placenticerus intercalari does occur in two forms representing male and female. This would be the male form. This is the micro-tant. Has these very, very prominent little nodes along the side, almost look like horns. The female is larger, and the nodes aren't quite as pronounced, but we do see this sort of node arrangement on the shell as well. But intercalari tends to be smaller than Placenticerus mici. They both, however, have this sort of almost frisbee-like form to it. And we have also straight-shelled ammonites, which we know as baculites, are the genus Baculites. These can get to very, very, very long, probably exceeding a meter long. This is what the fossil would look like. This is the body chamber where the animal would have been living inside the shell. And then this here we see part of the phragmocone that have these chambers in the back. Fairly common as well in certain areas are juvenile forms of this as well. It's kind of interesting that later on we would find that the juveniles probably lived in a bit of a deeper and different habitat than the adults did. And then we have this little guy in here that I call Baculites ovatus. I have my doubts about that now. I think it's a smaller version of Baculites compressus, but we'll go with this for now. In any case, it's very, very small, has almost like this belly-like shape in its body chamber, which is kind of bizarre. But anyways, that was interesting as well. And then we have the scaphites, which have this sort of hooked body chamber like this. These are like to me, are the coolest looking ammonites around. Many of them have nodes along the back and along the umbilicus. Again, have this sort of very distinctive hook on their body chamber. These are reconstructed as if they looked sort of squiddy. And there are three main forms, Rhinoceros, which has less of a pronounced hook at the end. Hoploscaphites, larger forms of this were called Gillette-sketes, now are recognized as another form of Hoploscaphites, but we have that one here. And then a smaller and flatter form, Hoploscaphites brevis. So basically we have frisbees, we have cones, and we have hooks. Now, is there a way, if we have ammonites living in the water column, is there a way of figuring out where they lived in the water column? Because we're talking, maybe up to 200 meters depth or so. Probably not, but maybe getting up to that point. There is a way of estimating at least the relative differences in where ammonites may have lived. We'll use a baculate in this case because they're the simplest. But we take a cross section of this. We can see that there are various dimensions that we can measure. We can measure the radius of the lobes and the saddles in the septa from the lateral view as well as from the front or back view. We can take all of these measurements. We can take a look at the thickness of the septum at a given spot, and we can actually estimate the maximum pressure that it would take, or the minimum pressure that it would take to implode implode the shell. And so this would then be translated to depth, to water depth, right, according to water pressure. So this is what we did. We made these calculations, took a lot of these specimens and measured all of the septa, take into account the tensile strength of nacre, that mother of pearl material. The calculations suggest that there's a wide range of implosion pressure and therefore a wide range of the depths of habitat. So as you can see here, so this is maximum habitat depth that was calculated based on implosion depth. And we can see that there is a range of depths. Now in here, we see that the frisbees, placenticerus, are up towards the surface. So this is water depth, right? Shallow water near the surface down to deeper water. So the frisbees we can see are at shallower depths. The cones, or baculites, are sort of in mid depths, and the hooks, or the scaphites, tend to be what suggests are at the bottom. So sort of shallow water, mid water, deep water. Another thing that I did was I thought, well, maybe interesting to take a look at stable isotopes. So the relative ratio of the isotope oxygen 18 to oxygen 16 is dependent on a couple things. One is the temperature of the water that the shell was presumably secreted at. And the other thing is salinity. So salinity can also exert an effect on what we call delta O18. What I've done here, so this is the delta O18 value of the shell material, of the nacre, and then this is sort of translated to temperature. So in here we can see the frisbees have a very light signature, and the cones or the baculites are sort of midway, and then the hooks or the scaphites sort of have the, I guess, closest to normal delta O18 value. So what this could mean, right, is that if we can think of water temperature decreasing with depth, right, it's fairly warm at the top and much cooler at the bottom. This sort of follows that pattern, right? It's fairly warm towards the top, cooler towards the bottom of the water column. But another thing that came about is that the values for placenticerus up here are abnormally light, like very, very, very light. So unless you're looking at temperatures up to 50 degrees Celsius, which are obviously unrealistic, what is something else that might be affecting that? Well, the other possible obvious thing would be salinity. So the fresher the water, the lighter the signature would be. Now we can sort of add another layer, if you will, on top of this and say that because this is in a fairly sort of restricted seaway, there would presumably have been, relatively normal salinity water coming down the seaway. But if you can imagine the runoff from land, right, as well as just regular precipitation, that if that stuff is falling into the sea, there would probably be a density stratification happening, where the more brackish water, so something that is a little fresher because it's lower density, would form a cap on top of the seaway, and the normal marine stuff would be obviously underneath that. This could, I'm not saying it does, but this could also suggest a freshwater or brackish water cap on the surface of the seaway. So as opposed to be a normal marine salinity, may have been more brackish, something that you may see more typically in an estuary or something like that. Both of those things together suggest that this is sort of the general distribution of ammonites by depth. Again, we have the frisbees on top, placenticerus. We have the orthocones sort of mid-water, and then we have the hooks down towards the bottom. This is just a display that I put up in the hallway at Western, and just sort of gives you a general impression of what the depth distribution may have been like. In mapping all of the sections of the bearpaw, looking at looking at rock type, looking at sediment type, looking at the types of environments, that sort of thing, that was one side. The other thing, while I was measuring that, was taking note of which types of ammonites were occurring along with these units of sediment. And even sort of right off the bat, you can see from this top layer here, which is basically that package represented by the Baculites residi zone, we can see that there are differences in where they're occurring. And in particular, the frisbees are occurring pretty much everywhere. The orthocones are a little bit more restricted, and then the hooks only occur in this particular zone, or basically only occurring in the southeast part of the province. Since that time, I've learned that they do occur very, very rarely over here, but again, are much more numerous down in the southeast corner, down in around the many berries area. So there does seem to have been a spatial difference in terms of where these forms would have lived. Now, also, if we can think about what may have been controlling this, why, for example, these ones were much more restricted geographically than these other forms were. So the forms, from thinking about this in a probably oversimplistic way, but if you think about like a bowl, right, basically a basin filled with water, if you were having forms that were at the top, you would and imagine they live, they die, they fall to the bottom. Those that were on the top should have the largest distribution, the widest distribution, right, because they're occurring everywhere. And so they die, they fall to the bottom, they're preserved there. Forms that are more restricted are more likely to have been sensitive to bottom water conditions, that are more likely to have been more heterogeneous, right? Because we have areas along the bottom that may have been better oxygenated than others. There may have been pockets that were not as well oxygenated and so on. Whereas higher in the water column, basically we're dealing with water that was more homogeneous because we would be mixing and that sort of thing. So taking all this information, putting it together, we can sort of think of a general picture that this might be representing. And this is it. So if we can take a look, take a cross-section across here, there's a sweetgrass arch in between. We have these ones that are very well distributed, these ones down here that are less so. And a little later on, the Cuniatus time, we have, again, these being well distributed, these not so much, mainly because of the restricted condition down here. And then we have this kind of situation where there was basically none of these over here. They're numerous over here and much less over here. This may have been because the bottom water conditions were dysoxic. There wasn't as much oxygen down there, and so weren't able to support as good of a diversity. Now, another thing that came about from the study is these holes, right? And probably most of you have heard of these holes now. So what is the origin of these holes? The sort of original study that was done by Earl Kaufman and Kessling, this is the original specimen, is that if you look at the pattern of teeth in mosasaurs, they pretty much match up very, very well with the patterns that we see in this particular specimen. Now, there was a bit of a wrinkle that was put into this because some researchers, including Kase, who was Japanese, interpreted these holes as having been dissolved by limpets, that these were limpet home scars, and that these were due to the sort of carving out of a lot of the shell material by limpets, and then being weakened areas would basically collapse in after they were buried. And Westerman and I disagreed with this, partly because of the arrangement of the holes. If we take a look at this is on either side of the shell. They match up fairly well. Also, we have these odd-shaped pairings. There's a large one down here, there's a smaller one down here. This may be either due to a crooked tooth or maybe due to also the way that the teeth were replaced. Here is a row here. This is fairly consistent with the row-like pattern that we'd see in mosasaurs. They have cratered rims. That was just impact with the crown of the tooth. And these double punctures, the way that mosasaurs replace their teeth is that we have a main tooth over here. We have a smaller one coming in sort of on the inside of it. And that may explain why we sometimes get these double punctures with one large one and one small one. And I think that was another convincing thing. Another thing is that there's some specimens that show evidence of repair. So we can see the outlines of some of these holes along here. We can actually see where a big chunk was taken out and the shell actually healed over. So this wouldn't, if this was due to limpets homing on the surface, we would still see a bunch of holes. And obviously, if this was done, this collapse occurred after the specimen was buried. Obviously, that ammonite couldn't come back to life and heal their shell. So that was another thing as well. Additional evidence, this goes back to the original specimens as well. Mosasaurs have their main teeth over here, and we can see that on the main specimen, we have these much smaller ones over here, which match up perfectly with the pterygoid teeth. And I think that's a bit too much of a coincidence to dismiss. Those that were sort of keen limpet were saying, okay, so the other thing is that limpets have been found directly sitting on the ammonites with some holes. And they said, well, if the holes were made by mosasaurs, why don't you find mosasaur remains turning up the same places as these ammonites with holes? Why aren't they held together? So as long as this is the case, that we don't find both of them together, we can't prove it either way. Many of you probably know that there have been mosasaur remains that have since been discovered south of Lethbridge and a few different times. One of the more recent one is here in 2022, found south of Lethbridge. I felt a little bit of indication when this particular one was found. So another thing about palaeoecology was interesting that along with some of these ammonites were these objects that were a black wrinkled film. At first, and being sort of the naive PhD student that I was, thought, well, these are plant remains, right? They're carbonized, as you would sort of expect like this. So here's a leaf, it's been carbonized, and it's probably something like that. But for the life of me, I couldn't find any plants that had any leaves of this particular shape. And so I sat on that for a while. It turns out if we take a SEM image, this is what plant tissue looks like when it's carbonized. It looks like this. So this is framboidal pyrite. And so it's nothing like this plant tissue. So it's obviously not carbonized material. So what could it have been? Looking at some other forms of ammonites, these turned out to be jaws. So this is the upper jaw of the ammonite, and this is the lower jaw, which is more scoop-shaped like that. And this is found in other ammonites of the same general group. So these vaguely resemble jaws of modern nautilus, but they lack the hard plates that are attached to it. See, so at the tip of the nautilus jaws, this is calcified, and so it can bite fairly robust prey. Ammonites also strengthen their jaws. So this is the upper jaw. So most of the jaw material itself is chitinous. In most cases, it's pyritized when it's preserved. This is the upper jaw, which is completely chitinous, which is now pyritized. This is the lower jaw, or the apticus. These are actually the plates that strengthen the jaw. So even with these, they look fairly robust, and so probably could have handled fairly robust prey. If we look at the scaphites, the hook-like forms, they also had a fairly robust-looking jaw. The jaws of the cones, of the baculites, also had a fairly robust jaw with these plates, and as well as a tip at the end. And also, that things have been found are the radula, which is basically a ribbon of tooth-like projections that, if we think of this as almost being like a tongue, and this sort of guides food to the back of to the digestive tract. Kruta and others found that this is the lower jaw, this is the upper jaw, actually found teeth of the radula that was actually found in here. These can be arranged like that, and does look like a radula of a modern mollusk. Interesting thing about this is that within this mess of radular teeth, some of the presumed prey was actually found. So this includes a isopod crustacean, and we have a little larval gastropod in here. And this suggests, at least with baculites, that baculites weren't actively pursuing prey like we would expect squid would be, but were actually perhaps almost filter feeding from the water column. So basically plankton feeders. Now going back to the jaws of Palaeoecology, here's the jaw over here. This is in Pierre Shale. This is the jaws that were found in the bear paw, and these do not have these calcified plates on them, and they look fairly flimsy. And when they're preserved, they have these wrinkles, these very prominent wrinkles in it. So could not have been that robust. This then begs the question, is there like a modern analog to these particular ammonites that were huge? They had to have been eating something. So what is an animal that is living today that lives near the in the near surface waters of the sea, is shaped like a flattened disc, feeds on soft prey, the ocean sunfish. So this is mola mola. This lives basically in the surface water of the sea. It has an unusual diet based on basically jellies, so jellyfish as well as salps. So its jaw isn't particularly well developed either. And this is sort of challenges this interpretation that ammonites were, just like an octopus or a squid that was these mean things that were going around and gobbling large active prey up, may have just been sucking up jellyfish. So is this a bizarre case of convergence? The similarities sort of continue. This is the upper jaw of a ammonite or a placenticerus. This is the upper jaw of a ocean sunfish. This is the lower jaw of placenticerus. This is the lower jaw of the ocean sunfish. In addition to this, ocean sunfish have pharyngeal teeth. They have teeth that are sort of almost like in their throat. And this will also sort of trap and guide food down to the digestive tract. We don't have any radula yet for placenticerus. I'm still holding out for that. This is the radula of Baculites, but presumed to have a radula, so probably had the same sort of function. So it's kind of a striking, it may be a coincidence, but it is a striking similarity. We know something about this ammonite soft body. This is one example of a ammonite. This is supposedly an ammonite soft body that was taken out of the ammonite shell by a predator and then basically sort of dropped, and it ended up being buried and preserved. Here are the jaws. The rest of this is kind of a hot mess, right? I could just say, well, we can clearly see that there's a crop in here, and we can see that this is reproductive organ over here, and we have the stomach over here, and I'm going, okay, sure. But it still requires a little bit of squinting and saying, well, it's not in the shell either, so it's hard to say, how valid this actually is. Another striking thing about this is that with cephalopods, we have fossil cephalopods of soft-bodied cephalopods. So this is an octopod from the Upper Cretaceous in Lebanon. Here is a fossil squid. You can see that we see the outlines of the arms. Here we have a fossil belemnite. We see the outlines of arms. Ammonites, nada, nothing. We do not have fossilized arms of ammonites. They have not yet been found. And it makes you wonder what is so fundamentally different from ammonite soft tissue that it's not preserved. The other possibility is perhaps ammonites didn't have arms. Other appendages. Now, we don't find arms, but there are some features that have been found. Here are some hooks that have been found in the body chamber of this Hophoscophites. And this is believed to have been from an appendage that most cephalopods had, which is called a heterocotylus, which is sort of the male organ that is used for mating. And here, this particular reconstruction has the arms in a net as opposed to as very distinct arms. That's a possibility too. In this example of Rebosterus, this is from Neil Landman's group as well. There are these complex hooks that have been found in the body chamber of Rebosterus, and these have been suggested to represent the hooks that were on the clubs of tentacles. So these long tentacles as opposed to arms. Possible. So back to the original question. Did they all do the same thing? No. Their habits were at least as diverse as their forms. Did they live in the same parts of the sea? No. Their places of living were at least as diverse as their forms. Did they live in different habitats? Yes. Their habitats were at least as diverse as their forms. So I'd like to sort of conclude. I hope I haven't gone terribly over time here. This is a recent summary of habitats of ancient cephalopods. Again, sort of when I started out this thing, there hadn't been a whole lot deduced about habitat. But as of 2021, this is sort of a summary of where we think different types of ammonites lived. It's certainly as diverse as what we see in modern cephalopods. If we think about the coleoids living today, basically the soft-bodied cephalopods that are living today, we look at all of the forms that occur in here, huge range in body form, body size, habitat depth, reproductive strategy, food type, the use of their appendages, how mobile they are. There is no reason to think that ammonites were any less diverse in any of these characteristics, and that includes habitat. And so even after 20 plus years of looking at ammonites, they still completely mystify me. We know a tiny, tiny little bit more than when I began I began that study for my doctoral thesis. So you might think about, this is what we think we know about ammonites, and this is what we want to know about ammonites, and we can probably extend that to paleontology in general. And please stay curious. This is something that has been a lifelong passion of mine, and I know that all of you, are very, very passionate as well. So, and this is what makes life interesting, right? Is to have your thing that you're interested about. Thank you for allowing me to give this presentation, and thanks for the invitation.
So put up your hand if you have a question.
When you look at an ammonite shell and you look at the earlier parts of it and then the later parts, you see some change. You were saying, at least for non-Lloyd, the
Young ones look like they were in deeper water. Is there a pattern that you could do looking at one shell of a change in habitat?
Actually, there was one that I didn't show here, was that there were a few shells that I looked at in terms of lifespan, right? So you can, baculites are very good for this because they're just straight. So you can just sort of sample down the length of the shell. And as it turns out, it appears that the younger the shell, the lighter the signature was, and therefore the deeper water that was living in. And as it sort of gets older, it sort of gradually, the signature gets, what we say is heavier, and therefore the temperature would have been gradually getting higher, and therefore closer to the surface. And I also looked at individual shells for septal strength as well, that sort of estimates depth. And sure enough, the young ones tend to have very strong septa, and the older ones actually tend to have weaker septa. So this seems to be, the general pattern seems to have been that the younger, the juveniles were living closer to the seafloor, and the adults were living closer to the surface.
I've got a question. So what are the estimates of
Like density in the water column and per square meter, per square kilometer. Are there any estimates like that? Because they are so prolific in the fossil record.
Yeah, that's a very good question, and I don't have an answer to that. So I don't think there is. You could you'd be able to figure that out. That's hard to say, unless you had one surface, right, that you can sample, that you could get all possible ammonites on that one surface representing a particular time. I think it would be pretty difficult to estimate that, unless you had a snapshot, right? Because when you're dealing with, even like a 1 meter section of shale, that represents quite a long period of time, and you'll only have, a few ammonites within that interval. Who knows how many were actually living at that time versus how many were actually preserved, right? So that's a difficult question to answer, but it's a very good question.
I just want to say a fantastic talk and really interesting research that you do. Just a question on nautiloids. Why do you think they've made it through the extinction event, whereas ammonoids didn't make it?
I think it comes down to specialization. To some extent. I think ammonites, well, partly also due to their diet. If you think about, a nautiloid can eat pretty much anything, right? They're sort of like the rats of the the rats of the Cretaceous seas, right? They can, if you look at the modern ones, they'll scavenge pretty much anything that's around. They'll eat pretty much any scrap of food. They also can live in much deeper water, so they can take refuge there. For ammonites, basically most of them lived in shallow water, and a lot of them seem to have been plankton feeders, right? So if we can think about the collapse that occurred at the end of Cretaceous with the plankton, right? You get rid of the plankton, we have these these animals that were specialized for maybe even eating certain types of plankton, and they would have been gone right away. And even if you look at the level of specialization, you look at the shapes of the shells and things like that and go like are you kidding me? Right? It's so ridiculously diverse that they seem to have been so specialized that that's probably what did them in.
All right. I have a question here for you. So this summer, I did some work in the uppermost dinosaur park formation.
Yeah.
There's a marginal marine unit in there, so it would have been kind of shallow marine
Is this the
environment.
tongue?
Sorry?
Is this the marine tongue?
Yes, exactly. The marine
Yeah.
tongue. So just east of the park. And
Yeah.
we recovered a little bit of ammonite material in there. And I'm just wondering if you're familiar with any previous ammonite material from that marine tongue, or what that
No,
tells us
I
about
have
the.
never heard of any ammonite material coming out from that. So that's very exciting. If you
Okay,
can
interesting.
figure out what would it be baculites?
I'm not actually sure. I'm a vertebrate paleontologist,
Okay.
so I don't have too much familiarity. But
If
maybe I can reach out.
Yeah, if they're baculites, then that would be worth gold because
Okay.
because it's still the baculite zonation is still has holes in it, and so to find out exactly which baculite zone that belonged to would be amazing to know.
Good stuff. Okay, well, maybe
Yeah.
I'll email you.
Okay, great.
These animals grow incrementally by adding a new chamber, which leads me to my question.
Yeah.
What is the longevity of a given ammonite or baculite? Like each segment, are they growing annually, monthly, or what?
In terms of the chambers, I don't know. It's been suggested that Placenticerus. It's been suggested that Placenticerus may have had indeterminate growth. So basically, it just grew as long as it could. Well, I know that there's some there are other ammonites, like for example, most scaphites actually definitely slowed down and probably stopped growing. So once that hook formed, the shell gets much more dense, and there's actually a lip that forms at the opening of the shell. So that is probably a point where it actually slowed down and was mating by that point. And I think that you can get that thickened aperture also in baculites as well. So they wouldn't have been growing forever either. If we're looking at something like a scaphite, I maybe think average scaphite probably under 10 years. That's just a sort of an intuitive answer. You may be able to determine that from growth lines on the shell, but that's something I haven't done.
So with the ammonites, there's that amazing iridescence. What creates that? Is it, and what is is it a variety of composition of the shell, or is it related to the recrystallization process or the interaction with the meteoric waters and that?
There may be some, I think there may be some diagenetic influence on that, and then partly as well because there have been some ammonites, especially in like south of Lethbridge area, that do have very peculiar geochemical signals. So for the stable isotopes, they're just really wonky. So I would think that probably there are some fluids that have influenced the composition to some extent. I don't know exactly how, but they are strange. The iridescence itself almost certainly is from constructive interference because of the layered structure. But there is also I'm actually working on some of that right now, and there is a diagenetic. Sorry, careful how I say this. There is a diagenetic change that happens that does alter the micro, or the, I guess it'd be nanostructure of those plates, of the aragonite plates. So it would be almost entirely optical, right? The effect, the iridescent effect, and it's due to it's something that is happening down at the microscopic level.
Yeah, hi Cam. Paul Johnston here. Thanks
hi.
for that talk. It was really, really interesting.
Thanks, Paul.
Modern nautilus fight one another apparently, and
Yeah.
they'll nip off the edge of the shell of their opponent. And so I'm sure you've seen on modern nautilus, some of the growth lines look kind of jagged and then repaired. Have you seen anything like that in any of the ammonites you've studied?
I would say that it's more common. Well, it's hard to say what is from an attack, like from predation or from fighting or whatever, from that versus just physical damage. But I could say that if you look at something like Placenticerus, I can probably give you like the number of examples that I've seen of a preserved edge of an aperture on Placenticerus is almost nothing. Almost all of them show some degree of damage, but whether that's due to individuals fighting with one another, or from from an attack from something else, or just from fragmentation on the seafloor, it's hard to say what caused that. But yeah, that's something is interesting is that very rarely in the bearpaw would you actually find ammonites with a complete aperture.
Yes.
And even
Yeah,
if on one side, and quite often on one side you'll see sort of a lip on it, and then on the other side it's jagged. So, and I don't know how one would actually answer that without having a very specific idea of the pattern of breakage.
Right.
Yeah.
Thanks, Cam.
Wonderful. Well, thank you again so much, Cam. And
Well, thank you for inviting me.